Alright, so here's our second example using the direct comparison test to determine if a series converges or diverges. So the theorem says let 0 be less than a sub n less than or equal to b sub n for all n. And if the series b sub n converges, then the series a sub n converges. And if the series a sub n diverges, then the series b sub n diverges. So to make this a little simpler where you can maybe understand it a little bit better, is you notice here this b sub n and this a sub n. Well, b sub n is the larger series, a sub n is the smaller series. So it's saying if the larger series converges, then the smaller series also converges. And this is saying if the smaller series diverges, then the larger series also diverges. Okay, so let's keep that in mind while we're working the second example here. You can check out my first example if you want. It should be close to this video. Alright, so we have summation n equals 1 to infinity of 1 over 2 plus square root of n. So I'm going to compare this to the series n equals 1 to infinity of 1 over the square root of n. Okay. Usually what you can do, you can just keep the largest term from the numerator and largest term from the denominator. So 1's the largest here in the numerator, and the square root of n is the largest term in the denominator. Remember, we're going to infinity. Alright, so I need to figure out what this series here does. I'm going to determine if it converges or diverges. So I've got the series n equals 1 to infinity, okay, of 1 over square root of n, which is equal to summation n equals 1 to infinity over equals 1 over n to the 1/2. I just changed square root to n to the 1/2. Now this right here is a p-series, and remember, for a p-series, if p is greater than 1, then it converges, and if p is between 0 and 1, including 1, then it diverges. So we can see here that p, this is p, your exponent. You can go and review your p-series if you need to. So p is 1/2, which falls into this category, so that means this diverges. Okay. Alright, so let's take a look at the two series, this one and this one. Okay, so we can see that 1 over 2 plus the square root of n is less than, okay, is less than 1 over the square root of n. Okay, so what we have here is we have the larger series diverges. Okay, the larger series diverges. So let's come over here and look at this again. This only says if the larger series converges, then the smaller series converges. And this says if the smaller series diverges, then the larger series diverges. But all we've shown is that the larger series diverges. So that doesn't meet the requirements of the direct comparison test. So what we can do is let's try comparing it to another series. Okay, so we compare to some other series, and we want something kind of in this form here. So we'll compare it to n equals 1 to infinity of 1 over n. Alright, And so let's see what this series here does. Well, it's the same thing. We can look at it as a p series. So our exponent is equal to 1. And remember, from up here, if p is between 0 is greater than 0 but less than or equal to 1, then it diverges. So we've shown that this diverges. Okay, and remember, we've shown this series diverges. So if that's the smaller series, that means we would show that the smaller series diverges. So that means the larger series would diverges. Okay, so we need to see if that 1 over n is if that series is smaller than our series we were given. Okay, we need to see if this series is smaller than this one, or see where it is smaller. So I'm going to see, okay, 1 over n less than or equal to 1 over 2 plus the square root of n. Okay, all right, so let's see what we've got here. How can we determine if this series here is smaller? Okay, well, that would mean that this denominator would have to be larger than this denominator. Okay, so we would have 2 plus the square root of n is less than or equal to n. Okay, if we can solve this inequality and see for what values of n that holds true, if it does hold true. Okay, all right, so let's solve this. So we need to subtract 2 to each side. So I've got square root of n is less than or equal to n minus 2. And then remember, we'll have to square both sides. So that's n is less than or equal to n squared minus 4n plus 4. And so I'll subtract n to both sides. So that gives me 0 less than or equal to n squared minus 5n plus 4. Alright, so let me just rewrite this. So that's going to be, I'm going to just rewrite it with my quadratic on the left hand side. And see how that's greater than, so that has to be the greater than or equal to 0. Alright, so we need to set this equal to 0. Remember how to solve these quadratic inequalities? So when we factor it, we get n minus 4, n minus 1, so we get n equals 4 or n equals 1. Okay, and so we can draw our number line, 1, 4. That breaks it up into regions, and I pick me some test points here. N equals 0, n equals 2, and n equals 5. So basically what I want to do is I want to see when this thing's positive. So I'll plug the 0 into here, so I have a negative times a negative is a positive, so this would be positive. Plug the 2 in, that would be a negative times a positive is a negative, and then plug the 5 in, that's a positive times a positive, which is positive. So we can see that this right here is true when n is greater than or equal to 4. Okay. All right. Now, how can we do that? Because we're determining the convergence or divergence from n equals 1 to infinity. Okay, you see that? N equals 1 to infinity. But here we have it's greater than or equal to this, or this is smaller than this when n is greater than or equal to 4. Well, the convergence of a series is not dependent on its first several terms. Okay, so we can kind of modify this and say n is greater than or equal to 4. Okay, so what we've shown here is that the smaller series, see, the smaller series here diverges. Okay, we've shown the smaller series diverges. And what does the theorem say? If the smaller series diverges, then the larger series diverges. And so that means by the direct comparison test, the series n equals 1 to infinity of 1 over 2 plus square root of n also diverges. And that is all of this example, and I hope it helped. Just remember, when you're using the direct comparison test, you have your theorem, and it may just be easier for you to look at it as the larger and the smaller, and the smaller and the larger. Okay. All right. So you can check out my other videos if you like this one. If you like them, you can subscribe. All right. Thanks.